Okay, hi everyone. In this video, I want to take you on the principle of mathematical induction. So let's go. Now, the principle of mathematical induction is used to prove that a proposition Pn is true. That is used to prove that a mathematical statement is true for all positive integers n, or for all positive integers n greater than or equal to k naught. Okay. So we do so in the following way. First of all, that these are the steps. The first one is that we prove that P1 is true. That means the statement must be true for n equal to 1. That statement is called the basis step. Okay, that's what we have here. Then the second step is that we assume that the statement is true for Pk. That means we assume that Pk is true. That step, we call it the inductive step. Then finally, we use the proof and the assumption to show that Pk plus 1 is true. So from the P1 and the Pk, we can go ahead to show that Pk plus 1 is true. Okay, it follows that Pn is true for every positive integer n. So that means, according to principle of mathematical induction, for a statement to be true, first of all, P1 must be true, P1. Okay, then second of all, the statement is assumed to be true for Pk. Then we can go ahead to show that it is also true for Pk plus 1. So that is the steps. Those are the three steps for principle of mathematical induction. Okay, so let's move. So we see the first question here. We have to show that the summation of R, I would like to explain that summation of R, which is equal to 1 plus 2 plus 3 plus dot 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 plus n, equal to n into n plus 1 all over 2. Now, I would like to say, first of all, when we say summation of R, okay, now R equal to 1 here means that R must start with 1. Then n here means that it must end with n. So in this case now, I want to explain what the summation sign means. So when R is 1, I put 1 plus this summation sign, this E sign here means summation. So you keep adding 1 plus 2 plus 3, like that. You keep going until you get to n plus n. Okay, let me quickly use another example, something else. Let's assume I want to find the summation of x squared. Want to give a little explanation for summation. And I have here x equal to 0, meaning that x should start from 0, then 4, meaning that x should stop at 4. The summation of this now, x squared, means I will start with 0, 0 squared, plus, then 1 squared, plus, then 2 squared, plus 3 squared, then plus 4 squared. Okay, and I can now add. That's exactly what that means. So we can stay 0 plus 1 plus 4 plus 9 plus 16. Okay, which should give us 25, 29, 30, which is equal to 30. Okay, so that is it for the summation sign. That's what that means. So when we say the summation of R now, sorry, let me rub this off. Let me rub this up quickly. Good. So when we say the summation of R is equal to 1 plus 2 plus 3 plus n, now you know what that means. Then this is the sum of the nth term. In when we treated AP and GP, sequence and series, we have sum of terms. Like for AP, we said that the sum of term of an AP is n over 2 into 2a plus n minus 1d. Okay, so we can use that. Or let me quickly use this. If you notice, this question, this particular series is an AP. How do I know? Because the first term there's a common difference. The common difference is 1. That's 2 minus 1 is 1, 3 minus 2 is 1, and so on. Okay, so if I substitute it here into my formula for AP, I'm going to get n over 2 into 2a. 2a means 2 times 1 plus n minus 1d. That means n minus 1 times your d is also 1. So that will give us n over 2 into 2 plus n minus 1, when you open the bracket, that's going to give us n over 2 into 2 minus 1 is 1, so I'm going to have n plus 1. Can you see that that's exactly what we have here? That's exactly what we have here. So that's to show you that the right-hand side is exactly what the left-hand side is talking about. So showing us that the total sum of that term is equal to n into n plus 1 all over 2. Okay, so that's, by the way, that's a little distraction. We are here to use induction to show that the left hand side is equal to the right hand side. That means the summation of r, when you start from r equal to 1 and end at n, you're going to get n into n plus 1 all over 2. Okay, so let's see the solution to this very problem. Now, we start by saying that let Pn be the statement that the summation of R is equal to this. We make that statement, okay? The next is we go into the basis step. Now, in the basis step, we pick the left-hand side. So the left-hand side here, the first term in the left-hand side, that's when n equal to 1. N equal to 1 means the first term. You can see that the first term is 1. That's the left-hand side. This left-hand side here. Here, this is the first term, which is n is 1, okay? So then for the right-hand side, you pick the right-hand side, which is n into n plus 1 over 2. If you substitute n equal to 1 there, you get 1 into 1 plus 1 over 2, which is equal to 1, you see? So from here, we can say that the statement is true for n equal to 1. Why? Because the left-hand side is giving us the same value for the right-hand side when n is equal to 1. This step is what we call the basis step, okay? You find the value for n equal to 1 on the left-hand side, and also find the value for n equal to 1 on the right-hand side. And you can now confirm that the statement is true, okay, for n equal to 1. Now, if after substituting the values are not the same, it means that you can't even go ahead with the principle of mathematical induction, because mathematical induction is just to show us that a particular statement is true, okay? So we continue. Now, the inductive step. In the inductive step, we are going to assume that pk is true. That means the statement is true for n equal to k, and proceed to prove that pk plus 1 is true. So by the inductive hypothesis, we have this, okay? If you notice, sorry, is blocked with my cursor, but look at it, you notice that it's the same thing, but except that n is now replaced with k. That's what we mean by assuming that the statement is true for n equal to k. That means when your n is now k, we assume that the statement is true. Now, we want to show that pk plus 1 is equal to k plus 1 times k plus 2 all over 2. That means when pn equal to n plus 1. Let me explain that. Okay, if you have n into n plus 1 over 2, and you want to substitute, wherever you see n, you put k plus 1, so you're going to have k plus 1. Then this n now becomes another k plus 1, then plus 1, everything all over 2. Now you're going to have k plus 1, then k plus 2 all over 2, which is exactly what we have here. So in solving for p k plus 1, we must get this. So let's quickly do that. So this is what we want to achieve. So let's see. So we want to show that pk plus 1 is equal to k plus 1 k plus 2 all over 2. That's the idea. Once we get this, we know that our statement is true. So let's continue. You see that? So if I put k plus 1 into the picture, in this case now, you see, I've added k plus 1 after k. Before now we had k, but now we after k, you have k plus 1. Just like after 1, you have 2. After 2, you have 3, and so on. So after k, you have k plus 1. So that's the reason why we added k plus 1, because we are interested in pk plus 1. And adding k plus 1 in the left-hand side means that we should add in the right-hand side for equality's sake. whatever you do in the left hand side, you also do in the right hand side. Okay, so that's why we have k plus 1 added to the right hand side. Okay, so we continue and we now solve the right hand side by taking the LCM. If you take the LCM is 2. So you have k into k plus 1 plus 2 into k plus 1, everything all over 2. And if I factorize k plus 1, if you notice here, k plus 1 is a common factor. So factorizing k plus 1, I'm going to get k plus, sorry, this is a mistake. This is meant to be, if I factorize, this is meant to be k plus 2. K plus 2, okay? That's supposed to be 2. It's supposed to give me k plus 1, then k plus 2 all over 2, which is exactly equal to p into k plus 1. Okay, sorry for that error. So as we continue, hence we can conclude that hence the statement is true for all positive integers. Okay, so let's see another example. Okay, look at this. We're asked to show that 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 equal to n squared. Okay, that means the summation of 2n plus 1 is equal to n squared. So let's see. We start with, let Pn be the statement, that 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equal to n squared. Okay, that's repeating the statement. Then we'll go with the basic step. Basic step, n equal to 1. Okay, now the left hand side, n equal to 1, that's the first term is 1. You can see the 1 here, that is the 1 here. Okay, then we go with the right hand side. The right hand side is n squared. When you substitute 1 for n, you are going to get 1, you see. So you can see that the left hand side is equal to the right hand side. Okay, so we can conclude that the statement is true for n equal to 1. That's exactly what we are going to conclude. The next thing is the inductive step, which is for n equal to k. Now it means that replace all the values n with k, and that's, we say assume that pk is true and proceed to prove that pk plus 1 is true by inductive hypothesis. So you see what we have here? The same thing, except that your n has been replaced with k. Okay, so the next is for k plus 1, n equal to k plus 1. Now remember what I said in the previous question, that when it was k, we ended with 2k minus 1. Okay, that's the kth term. 1 is the first term, 3 is the second term, 5 is the third term. Then that means the kth term is 2k minus 1. Okay, so now for n equal to k plus 1 means we should go a step further, and we are going to have this. So watch. So you notice, see what we added to the left hand side here. What that means is that replace k, wherever you see k in 2k minus 1, replace it with k plus 1. So you have 2 into k plus 1 minus 1. That's exactly what we did there. And because we added it to the left hand side, we should also add the same value to the right hand side. Remember, how did we get this? Is by replacing k here, this k here with k plus 1, and we get that. When you say 2, then we have 2k minus 1, okay? And you want to replace the k with 1, is going to be, it's going to be 2 into k plus 1 minus 1, and that's exactly, what we have there. So adding it to the left hand side, whatever you do to the left hand side, you must also add to the right hand side. I hope you understand that. Okay, so that now leads us to the next point. We have solved the right hand side now. So we solved the right hand side. When you open the bracket, you're going to get 2k plus 1, and which is this k squared plus 2k plus 1. Then you factorize, you're going to get k plus 1 squared. Now I want you to notice that k plus 1 squared is the same as when you substitute n equal to k plus 1 into kn. Look at this, look at your k plus 1 here. Look at your n here, sorry. If I put k plus 1 here, I'm going to get k plus 1 squared, which is exactly the same thing I got here by my inductive hypothesis. So we can now conclude that the statement is true for all positive integers. So you are going to conclude when, after substituting value n plus 1 into pk, after substituting n plus 1 into pn, That's your Pn here. Watch, your Pn here is equal to n squared. So if I put pk plus 1, is supposed to give me k plus 1 all squared, okay? Squared. And that is where your hypothesis should lead you to. You see, my hypothesis led me here, and we have this. So once I can establish this, we can conclude that the statement is true for all positive integers. Okay, so let's move on. Wow, we see